Okay, hi guys. So I just wanted to start off and talk a little bit about just graphing basic sine, cos, and tan functions. We're going to begin just by, I'm going to draw a little unit circle here, just that we're going to refer back to as we're going. So here's my unit circle. It's terrible as usual. Okay, so we know at 0 we've got coordinates 1, 0. At 90 or pi on 2 we have coordinates 0, 1. At 180 we're at negative 1, 0. And at 270, 0, negative 1. Okay. The other thing I want to do is I'm just going to underline in red the sine or the y part of the coordinate. And in green, I'm just going to underline the cos. Okay, so our graphs are as follows. So we have y equals a sine b bracket x minus c plus d. That's for sine. For cos, exactly the same. Oh, I've got the b. B x minus c plus d. Okay, and in these graphs, this a corresponds to our amplitude. B is our function for our period, C is our horizontal, and D is our vertical transformations. Okay, same with cos. For tan, we still have all the same transformations, but because tan is a very vastly different shaped function, then they are going to look a little bit different. Okay, so I just want to start off, I just want to show you guys the graph. I'm just going to use my graphing calculator. And I'm just going to show you the graphs of sine, cos, and tan. All right, we'll talk through that, and then we'll go through some of the transformations. So we got sine of x, cos of x, and tan of x. Alright, I'm just going to set up my window to go to 2 pi. My x scale, I'm going to chuck that as 0.5 pi. Alright, and now we should graph and we should see, okay. Actually, I might just turn that. These are two off just for a sec. I'll turn them back on again in a minute. Alright, so in the graph we can see that at 0 we have coordinate of 0, alright, and that loosely corresponds to, or exactly, not loosely, exactly corresponds to the fact that on your unit circle, your sine coordinate or your y coordinate is 0 at 0. Okay. For our, we then reach our maximum point at 90 degrees, go back down to 0 at 180. At negative 1, we're at 3 pi on 2, and then we return back to 2 pi. If I just turn on my cos graph, we can see that we've just got a horizontal shift of pi on 2 for cos. So cos and sine are actually the same function, just with a horizontal shift of pi on 2. So we can see that that x-intercept there is at pi, in cos it's at pi on 2, so we've had a shift to the left of pi on 2 units. We start at the maximum point, we go down to the minimum point, we return to the maximum point. And again, that's because on our unit circle, cos has a value of 1 at 0. If I switch on tan, we can see that with tan, we start at 0 and we increase, and that increases exponentially up to infinity. We don't have a restriction on our range for tan. We then start, after we hit that asymptote at pi on 2, it then decreases down, and then we have that another wave shape coming through here. We then have another asymptote at 3 pi on 2, and then it's going to start repeating again from there. If we look at our unit circle, again, this kind of makes sense because we know that tan equals sine divided by cos. So again, if we look at our unit circle, 0 divided by 1 is 0, so that's why at 0 again, tan starts at 0. But we then hit 90 degrees or pi on 2, which is where that asymptote was. and 1 divided by 0 is undefined. So that's why we have that asymptote for tan at that point there. Okay, so I just want to talk through what each of these A, B, C, and D do, and we're going to draw a graph, and then I'll show you on the graphing calculator with tan and cos as well. Okay, so if we just look at, say, y equals 2 sine of x. Okay, so we're changing that A value. Now, if I put it in my calculator, okay, 2 sine of x, we're just going to see that we get double the amplitude for that function. Okay, so our cos has stayed the same because that's still just cos of x, but 2 sine of x increases up to positive 2 and decreases down to negative 2. Again, we can relate this back to our unit circle, because with our unit circle, that would just mean that we would have our circle would be double the size of what it is here. Okay, we're just increasing that radius out to being 2. All right, so if we're drawing the graph, and because we're looking at sine, I'm going to use red, come on, red. Okay, again, sine starts at 0, 0, so we're starting at 0, 0. We're then hitting our highest point at pi on 2. Now, because this is 2 sine x, our amplitude is 2. We're then decreasing at pi, back over here, back down to 0 again, that y coordinate. And at 3 pi on 2, we're down at negative 2. Okay, and then at 2 pi back to 0, because we've done one full rotation of our circle. Right, so if we join all these up, we're going to get our nice sine curve, beautifully drawn, exactly symmetrical as you can see there, and that's our sine graph. Okay, if, for example, we were, instead of graphing 2 sine of x, we were going to graph this orange, we were going to graph y equals sine of x plus 1. Okay, we now have a vertical shift here instead of an amplitude change. So we're shifting everything up 1. So here we've got a rotational axis which is around 0, 0. But if we wanted to shift that up by 1, that's just going to move that rotational axis up once. So all of our main points are going to be the same. We're still going to start at 0, but now we're going to start at 0, 1. In this case, we've got an amplitude of 1 because there's no coefficient in front of the sine of x. So we're going to be increasing up to 2. We're still at pi, but instead of going through 0, we're going to be at pi and 1. That can be that middle coordinate there. 3.2 is still the lowest, but again, amplitude of 1, so we're just going to have our change of 1, so we're just going to be looking at 0. And then at 2 pi, we're back to where we started from. So this would be our sine of x plus 1 function there. Cool. All right, I'm just going to quickly erase this, and then we'll do some of the other ones after that. Alrighty, so say now we're going to look at our, say we're going to look at y equals sine 2x. Okay, so again, in this case, amplitude's still going to be 1. There's no horizontal translation, so our rotational axis is going to be at 0. Okay, but in this case, we are doubling our frequency of our function. Okay, this is doubling our frequency. It's a horizontal kind of, so we're at horizontal dilation, and it's doubling it. So it's going to become more squashed. It's going to be closer together. And again, you can think about it as doubling the frequency. I quite like that. So originally, our sine graph has intercepts at pi on 2. Highest point at pi on 2, intercept at pi. Lowest point at 3 pi on 2, and finishing at 2 pi for first rotation. If we're going to be doubling that, we're going to have twice as many kind of key points. So I'll use pink. So instead of our highest point being at pi on 2, it's going to be half of that, which is pi on 4. So we're going to have pi on 4, Okay, that's where we're going to reach 1. We're then going to go back through pi. Okay, that's the next point. That's going to be our x-intercept. We're then going to be halfway again between pi on 2 and, so highest point at pi on 4. Then we're going to have an intercept at pi on 2. Then we're going to be halfway between pi on 4 and pi, which is 3/4 pi, is going to be our lowest point. Okay, down at -1. Then at pi, we're going to be back to 0 again. So this is going to be 1 full rotation. We'll draw it in here. Okay, then we can draw the next one. So halfway between pi and 1.5 pi is 5 on 4 pi. Again, that's going to be back at our highest point. And then halfway between 1.5 pi and 2 pi, we're going to have 7 pi on 4. Okay, so that's me down here. All right, so here we go. There's our double frequency graph there. All right. Last one we're going to look at is if we have a horizontal shift. So if we have a horizontal shift, say we're going to look at sine of x minus pi on 4. Okay. This is what you've got to remember, whenever you've got a negative horizontal shift or a horizontal change, that's moving all of your values to the right, not to the left. Negative moves to the right, positive is going to move it to the left. So if we look at this function here, we're shifting everything pi on 4 to the right. So our basic graph's going to be the same. I'm just going to mark the points on again. So we're going to have 0. Highest point's going to be at pi on 2. Lowest, we're going to have an intercept at pi, again there. Lowest point's going to be at 3 pi on 2, so down here. And then we're going to be back to 2 pi at this stage here. So highest, middle, lowest, back. Okay. Now, if we're shifting everything to the left by pi on 4, so if we're shifting everything to the right by pi on 4, that means that all of these are just going to move pi on 4 across. So our starting or our intercept is going to be here. That means that we're going to be coming up to that intercept at this point here, okay? Because you've got to imagine that this graph is keeping on going down here. So that's going to be parallel with that there. Right. We're then going to be coming pi on 4 units across for our highest point. So that's me up at 3 pi on 4. We're then going to be another pi on 4 units across for our x-intercept. So that's going to be 5 pi on 4. 7 pi on 4, we're going to reach our lowest point. And back at 2 pi, we're not going to quite have made it all the way up again. So that would be our horizontal change by pi on 4 there. What I would suggest is that you guys go through and you have a look at a lot of these on GeoGebra, and you really pay attention to what these period changes and stuff do. I just wanted to quickly show you some of these with cos and tan. So cos obviously is exactly the same. So if we put all this together, we are say going to have 3 cos 2x, say, plus 1. Okay, so in this case, we're going to be doubling the period, amplitude of 3, and vertical shift of 1. So if we graph this, and I'm going to need to change my window just a bit bigger. So we'll go from negative 5 to 5. Okay, if we graph this, we can see that our rotational axis should be through 1, which is good there. We've got an amplitude of 3, so we're going 1, 2, 3 units up, 1, 2, 3 units down. So that's our highest and our lowest points there at 4 and at -2. And we're also doubling our frequency. So we've got, that's pi there, that's 1 rotation, and another pi, that's another rotation. If we look at tan, tan's changes are a lot more subtle because it does work differently to the other trig functions. So you'll notice that this 2 here, that is going to double the frequency of tan. We're going to have twice as many lines as we would in our regular tan graph. I'll just graph the regular tan graph as well so you can see that to compare it. But that 2, that vertical, because we've got an infinite range, that 2 actually isn't really going to do anything. I'll add on a +1 as well, and you'll see that that's just going to move that all the tan graphs, they have that like that point of inflection where it